Okay, on to part 3 or topic 3 of electrochemistry. You'll notice I'm wearing my yellow shirt from Sri Lanka, so I think I'll have to send Dr. Loeb these videos because he always calls me Charlie Brown when I wear this shirt. So I'll send Ed Loeb a link to these exciting lectures. And so it'll be part 3, topic 3. Remember, we're not doing topic 4 this chapter. So the last one is, I'm excited, you can tell, yes, there is another way to calculate delta G. So we'll take the voltages we calculated in part 2 and the number of electrons transferred, we learned how to count in part 1, and combine them to calculate delta G. And so as I mentioned earlier, electron flow is spontaneous when you have a positive voltage. And so that will give us another way, we'll see, to calculate the delta G. In the formula right here, N is the number of moles of electrons moved in a balanced equation. I mentioned in topic 2, the voltage only depends on the ingredients, but the number for N will depend on the balanced equation. So the voltage is determined just by the desire of one ingredient to give electrons to the other ingredient. The quantity of materials you have will ultimately determine the value of the energy that you're releasing or using. And so this will actually depend on the balanced equation. So N is the number of moles of electrons transferred. F is a constant named in honor of Faraday, and that'll be given to you, of course. It's 96.5 kilojoules per volt mole. And so, thinking back to chapter 17, there won't be any exception here. If that means spontaneous, then we look at the formula up above. Delta G equals minus NF E naught cell. That means delta G will be negative. And so there are no exceptions there. I'm not underlining that. That's a large negative sign. When we look at delta G here, this is going to be, you notice the units on here. This is moles of electrons. The voltage comes out right here. That's the unit on E naught cell. It's in volts. You notice how things cancel. The unit will come out to be energy. We have to be careful. It's going to be in kilojoules. If we're calculating a value of K, then sometimes that constant R is in joules. We just have to be careful. That'll come out to be kilojoules. So let's do a practice problem using this equation. Delta G equals minus NF, constant, Faraday's, times the voltage. And in this problem, I give you the voltage. .62. So please pause the video, try to calculate it yourself. Keep in mind you have to know the value of N. Here's the math on this. Delta G naught equals negative. N in this case is 3 moles of electrons in that balanced equation because the aluminum loses 3, iron 3 plus picks up 3. So that's 3 moles. Faraday's constant is up above, so I'm just going to write F. That's the 96.5. And then I multiply by the voltage, 1.62 volts. I better check my notes to make sure I have the right answer. Comes out to be negative 469 kilojoules. And that's for the balanced equation as written. We can phrase that like per mole of aluminum. We can phrase it per mole plus, but that negative 469 goes with that balanced equation. So like I said, you could phrase it like per mole of Al if you wanted to, but the number itself goes to the balanced equation. If we somehow change these coefficients to 2's, then this becomes 6 and we would double the energy. So thinking back to chapter 17, we looked at 3 ways to calculate delta G, and we're going to compare the methods here. One of them was delta H minus T delta S. If we want to be linear, we can just do it in the same order we did in the last chapter. This is the summation of the formation of all the products minus all of the reactants. And then there is the other method, RT, LNK. So those were the 3 methods we used earlier. Now we have a 4th tool in the toolbox because we can use minus NF E naught cell. And what we're going to do in our next practice problem is we're going to compare 2 methods, and you'll see they have to come out to be the same, because no matter what you calculate delta G naught by, if you're doing it for the same reaction, no matter if you have a K value or you have H and S, it must come out the same, because delta G is delta G. And so we're going to try 2 methods. Method A uses some information from the back of the book. It's the delta GF values. I have them here on the screen. And so you can also look at page A11 in the back of the book. But here they are, and it's for this cell. We have to make sure we have the correct balanced equation. This is a problem we did earlier. We did this cell, we turned the shorthand into a balanced equation. Remember, the reactants are the first and third items. So there's an Ag plus on the reactant side. This one comes up very nicely balanced because the sodium loses 1, the silver ion picks up 1 electron, so that's all balanced out. And so everything is a 1. And so we can do our products minus reactants. 2 of the materials have 0 values. The Ag solid and the Na solid. Elements are 0 in delta GF terms. And so we just take the sum of the products, which is just going to be negative 261.9 keep all my units on there. It's going to be negative 1 mole times negative 261.9 kilojoules per mole. That's the products of this. Reactant side. There's 1 mole of Ag plus. Its value for the back of the book is 77.11 kilojoules per mole. My moles cancel, and so then I get a combined value. Double check my notes. Negative 339. I just rounded off. I guess technically it's 339.01, but I just called it, forgot my negative there. Sorry, it's negative 339 kilojoules officially for the reaction, but since there's a 1 on that balanced equation, you can could say like per mole of Na, but officially, this is how it comes out. Like I said, it goes to the balance equation. You could write like per mole of sodium, per mole of Ag+. But there's our value, negative 339. We're going to compare that using voltage. So, and we know within rounding, it's going to have to come out the same. And so, there's our voltage formula. And so, number of moles of electrons moved is only 1. Faraday's constant is 96.5 kilojoules per volt mole. Okay, now we need the voltage from the table. If you have your notes booklet, it's on page 13. And so, when we look at that shorthand notation of the cell, the silver is the cathode, so it's at the very bottom of my screen. So the voltage of this cell is the cathode. .8, I just take it right out of the table, minus the value of the anode. You see the sodium out there wants to get rid of electrons, so there's a big gap here. It's negative 2.71. So if you were to punch that in your calculator, you would get 3.51 volts. So for example, you can make a 3.5 volt battery out of sodium and silver. And so we punch that all in. And it comes out with just a slight rounding difference. I get negative 338.7 kilojoules. Releases a lot of energy because there's a big gap in potential. Once again, this is for the balanced equation as written. So you could phrase that like per mole of sodium, per mole of silver ion, because this goes with the entire balanced equation. But it releases a lot of energy, and it's this, within rounding, it's the same number we got using the textbook values for delta GF. Connecting back to chapter 17, since delta G is negative, that means it's spontaneous. Think about the K value here. Should it be a big number or a small number? It will be a large value because anytime you have a spontaneous reaction, the product side dominates. So in this case, the Na plus and the silver solid would dominate the equation. Would go to the right side spontaneously, and we're going to calculate that number to show it's big. So this, once again, jumps back into chapter 17, where we have that formula, which is basically turning the delta G equals minus RT ln K backwards, and we do K equals E, the exponential function, to the negative delta G over RT. R is the gas constant with different units, 8.31 joules per mole per Kelvin. The temperature in all these problems is 298 Kelvin. And so the units on the delta G, since we said it was for that reaction with like a mole of sodium, we can say it's like negative 339, or you can use 338.7. Use either one. Get slightly different answers. We have to watch the units though, because we have to make this in joules. And So I'm going to use the first one. I'll say like joules per mole of Na. And so I have to then joules. And I'm going to divide by the 8.31 per mole per Kelvin. That's multiplied by the temp. Watch your brackets here. And so we punch that all in. Watch your signs here because you've got two negatives. That's a positive then. And so when you do that one, you should get 2.83 times 10 to the 59th. Remember, that's a ratio. That's telling you that at equilibrium, there are 2.83 times 10 to the 59th products for every one reactant that's left, because K is products over reactants. That's a big number. If you use, just to make you not worry about rounding, when you do exponentials, the rounding can make a big difference. If you do the 338.7, you'll actually get 2.55 times 10 to the 59. So when you start rounding and doing exponentials, it actually significantly changes the number. They're both correct because they're both values of delta G. But like I said, if you decide to use the 338.7, I think you get 2.55 times 10 to the 59, but either one is correct. The last thing we'll cover here is just looking at a possible shortcut. Because in the problem we did up here, you could have calculated delta G by finding the number of moles, and then you find the voltage. And then we do part 2, where we end up using that formula. There is a shortcut formula that I won't really go through the whole derivation, but you'll see it in the book. They use base 10 logs, I use natural logs. But if you want to, there's just a shortcut because, you know, these two are equal to each other. And so, you know, ultimately minus RT, ln K, if I put boxes here, you know, these two are equal. They have a lot of constants in them, and so there is a shortcut formula. You're basically solving these two. You're putting these next to each other. You solve for K. Look at that mess. E to the NF E naught cell over RT. Thankfully, there are 3 constants in there. F is a constant, Faraday's. R is the 8.31. Our temperature will always be 25 Celsius or 298 Kelvin in these problems. And so there's a shortcut formula. When you put all those constants in there, it just simplifies. It doesn't look that simple, but trust me, it is. And so there's the shortcut formula. It's basically the blob above it with constants in it. So the value of K equals E to the N, because that can change. It's different for every reaction. Number of moles of electrons moved. The voltage changes, obviously, because it depends on the ingredients. And then you multiply those two together, divide by this constant, 0.2566 volt moles, and then you'll get the K value. And so that constant is F divided by RT. So if you do that in your calculator, you'll get 0.2566. And then if you want to check your math, here's the problem we just did. 1 mole times 3.1 volts divided by that constant, 0.2566. And if you do it on your calculator, you should get something that approximates the 2.55 times 10 to the 59. And so before I turn you loose on some problems, I want to do problem 30 on page 70 together. And then we're going to do 32 with it. And so what it's asking you to do is use the data on page 13 in your notes booklet to calculate delta G for this reaction. And so this is where the electron counting that I asked you to do in topic 1 will come in handy. And so here's the formula. Delta G naught equals minus n, number of electrons moved, times Faraday's constant, times the voltage. So the two things you need to find are n and E naught cell. And this is where, like I said, the counting was more important for me than anything else. So when we look at this equation, I would focus on probably the tin, because it starts off with a 0 charge. I think they're easier. Each one of those tins is 0. This side, each of those tins is a plus 2. They each change by 2. And so 3 times 2 is 6. And so for this balanced equation, N is 6 moles of electrons. F will be a constant, 96.5 kilojoules. If you looked at the F's, you'd get the same thing. You get the 6 because these are balanced. So now we need to know the value of E naught cell. The other thing that should be apparent, if we look at those two boxes up there, that's an oxidation. So when we go to page 13 to get some data, that will be the anode. And so when we go to page 13, this will be the cathode, the iron. So when we get values off page 13, you go right to the table. Since that's a reduction, you grab its value off the table. You have to be careful. There's some iron, there might be several iron items in there. You have to get the iron 3 going all the way to iron neutral by gaining 3 electrons. So in the table, the iron value is negative 0.04. And so the E cell for this problem from page 13 is negative 0.04 volts. And then we find the tin reaction. It's not very far from the iron in there. We want the tin 2 reaction. In the table, that's negative 0.14. It's a little above it. We type that in our calculators. The voltage of this cell is not much. It would be, if you made a battery out of this, the side of the battery would say 0.1 V. And so we make a 0.1 volt battery. We'll still get a negative G out of this, but it won't be as much as some of the other reactions. So we multiply that together, F is 96.5. For this question, you should get negative 57.9. The units come out to be kilojoules, because that's the unit on F. And that's for the balanced equation as written. You get negative 57.9. Okay, that's 30 part A. If you look downward in the book, 32 tells you to go back to problem 30 and do the K value for that reaction. So it's just wanting the K value for that. And so I'm going to ask you to do problems 29 and 31. They're paired problems. 30 and 32 also go together. And so it tells you to go back to part A of number 30 and calculate the K value. We know the delta G already. It's negative 57.9 kilojoules. We're going to have to do a little cheat on the units that kind of go beyond the scope of what we do, but don't worry about the moles piece. When we calculate the K, you just put in the G, and so we can use that one. K equals E to the negative delta G naught over RT. Watch your units, because remember this is in joules, 8.31. There's a negative in the formula. There's also a negative on the value for the delta G. That's the negative 57. And it's going to be negative 57,900 joules. Temperature is 298. So type all that in on your calculator and hit pause on the video. And then when we come back, I'll put the answer on the screen. Here's the K you should get. 1.43 times 10 to the 10th. So it's a large positive number. And so that's the K value. You might have slight rounding differences, don't worry, as long as you're close. And so that's the K. You can also use that shortcut where K equals E to the N, which, if we go back to problem 30, the N is 6. The E naught cell is 0.1. You divide by the constant, you might have some rounding differences, but you can use that shortcut. But I like problems 30 and 32, and also 29 and 31, because they take you more step by step. And so here is some practice on topic 3. This will end chapter 18. We are over the hump, so to speak, on our material for the rest of the semester once we finish 18. And so try those page 19 outside of class follow-ups. So there are some practice problems on page 19. Question 8 on 766 is good. And I think these book problems are really nice. 29, 31, and you see a few others on 770, 74. And then we will not be covering pages 20 to 22 in the notes booklet, so you can freely cross those out. If you want to do wiggles or dig into that page, whatever you feel like doing, we are not doing those pages 20 to 22.